Welcome back to part 1, section 2 of our study of atomic spectra and the Bohr model. So hopefully you had a chance to run the PhET simulation and you have something of an idea of what's going on here now. The basic idea is this. If we think of our atom as having certain discrete energy levels that the electrons exist in, and as the electrons move from one level to the other, they gain or lose energy. And if only certain levels are allowed, then that's going to explain why we only see certain frequencies or wavelengths of light being emitted or absorbed by the atom. If an electron goes from a higher energy level to a lower energy level, it's going to emit energy. And if an electron goes from a lower energy level to a higher energy level, it's going to absorb energy. Now, it's nice to draw these little circles, but sometimes it gets tiring to draw these circles all the time. So what we're going to do instead is we're going to use a simplified diagram, where we're just going to have horizontal lines corresponding to energy levels. So, when an atom absorbs a photon of light, what's happening is an electron is jumping from the lower energy level to the higher energy level. But because the energy levels are certain distances apart in energy, only photons with the exact right amount of energy will cause an electron to jump up to the higher energy level. Here I'm picturing it with our lines model of the energy levels. Now, emission is just the opposite. When an electron in an atom goes from a higher energy level to a lower energy level, it emits a photon. And the energy of the photon, i.e. the frequency of the photon, is determined by the energy difference between the two different levels. The energy of the photon that's emitted must match exactly the energy difference between the two energy levels. Now, when this happens spontaneously, it happens at some random time. We can predict the probability of it happening, but we can't say exactly when it's going to happen because it is a probabilistic process. Now, these energy levels are different for every different type of atom. Therefore, the wavelengths of light that are given off or absorbed by different atoms will be different. So this is going to explain that unique emission spectrum, that fingerprint that different atoms are going to have. Now we can actually derive Bohr's formula for the radii of the different energy levels in a hydrogen atom using the Rydberg formula. We're going to need the following things. So here is your chance to look back on these formula if you don't remember them. We need to know the potential energy of two charges. And we need to know Coulomb's law for electric force. We learned about both of those things in the unit on electrostatics. We also need to remember a formula from last year's physics, the formula for centripetal acceleration. And finally, we need to learn about that formula we learned about in this unit, namely Planck's formula for the energy of a photon. We learned about that when we talked about black body radiation and the photoelectric effect. Okay, so if you didn't get a chance to go back and research all these formulas again, here they are just for your convenience. The electric force, Coulomb's law force. We're talking here about the attraction between a proton and an electron. This is a hydrogen atom, and so we only have two charged particles in a hydrogen atom. One of them is positive, the other negative. We don't care about the signs of the charges, at least in calculating the force. Because we're going to end up getting the charge magnitude squared times Coulomb's constant divided by the radius of the orbit that it's going in squared. We also need to know the centripetal acceleration formula, the centripetal force formula, which if you recall from last year is mv squared over r, where v is the speed of the particle in its orbit, and m is its mass, and r is the radius of the orbit. Well, the basic idea here is that the centripetal force is the electric force. The electric force is what's causing the electron to go around in a circle. So we just equate the Coulomb force, Ke squared over R squared, to the centripetal force, and we do some manipulation, and we notice that if you multiply both sides of that equation by a half, and you get rid of one of the r's in the denominators, you're left with 1/2 mv squared on one side, which is the kinetic energy. So this shows us that the kinetic energy of this electron going in a circular orbit is 1/2 Ke squared over r. Now the potential energy of two charges is given by the formula K Q1 Q2 over R. Here again, the charges are both the fundamental charge. One of them is negative though, and that does give us a negative potential energy, which is what we expect. If we have our zero for potential energy out at infinity, then as the particles come closer together, they are losing potential energy, so we should expect a negative potential energy. So the total energy of our electron in a circular orbit is going to be equal to the potential energy, which is a negative Ke squared over R, plus a positive 1/2 Ke squared over R that we got from the kinetic energy, meaning that the total energy in our hydrogen atom is a negative 1/2 Ke squared over R. We can use the Rydberg formula to describe the energies of the photons that are emitted from the hydrogen atom. Let's go ahead and modify the Rydberg formula slightly by using Planck's formula for the energy of a photon. Remember, the energy of a photon was Planck's constant times the frequency. And we know that since this is light, the speed of light is equal to the frequency times the wavelength. So the frequency is equal to the speed of light divided by the wavelength, which means the energy of a photon is Planck's constant times c over lambda. That's 1 over lambda. That's convenient because in the Rydberg formula we have 1 over lambda. So we can just multiply both sides of the Rydberg formula by hc, and that'll give us a formula that says that the energy of a photon is equal to hc times RH, Rydberg constant, times the quantity 1 over n1 squared minus 1 over n2 squared. Or, bringing the constants into the parentheses, we have hc times Rydberg constant over n1 squared minus hc times Rydberg constant over n2 squared. Let's take a look at that formula then that we get for the energy of a photon being emitted in the hydrogen spectrum. The energy of a photon is a difference in two other energies, and each of those other energies is described by an integer, and any pair of integers is going to give us a photon that is one of the allowed energies of photons being emitted in the hydrogen atom. That seems to suggest that those two different energies are in fact the energies of the electron orbits themselves. So if we take those energies that we got from the Rydberg formula and equate them to the energies of the different radii of orbits in the Bohr model, we get this formula. And if you solve all that out, what you find out is that the radius of an electronic orbit in a hydrogen atom is given by this formula here. Coulomb's constant times E squared times N squared over 2hc times the Rydberg constant, and N is an integer. We could rewrite that formula like this. We could just say that the different radii that are possible in a hydrogen atom are equal to n squared times a naught, where a naught is the so-called Bohr radius, and n is the integers 1, 2, 3, etc. This Bohr radius is all the other numbers in the formula that were constant, Ke squared over 2 Planck's constant times speed of light times RH squared. And it's a distance of about 0.53 times 10 to the minus 10 meters. Now, the Bohr model works really well for hydrogen. It works less well for other atoms, and in fact, the larger the atom gets, the less well it works. We no longer use the idea of an electron going around in a circular orbit to explain the structure of an atom. But Bohr's idea was very powerful because, as I said before, it was the first one to quantize the different energy levels. But one can actually calculate Bohr radii for the energy levels of other atoms. All you need to do is to take the formula for the radii in the hydrogen atom and divide it by the atomic number. So you have here the radii for an atom would be the Bohr radius times n squared over z, where z is the atomic number, and n is the positive integers 1, 2, and 3, etc. Once you've actually calculated the Bohr radius, it becomes quite simple to get the energy levels for hydrogen, at least the radii of the energy levels. R1 is the Bohr radius. R2 then would just be 2 squared times that, so it's going to be 4 times the Bohr radius. And then R3 is going to be 9 times the Bohr radius, 3 squared.